Okay.
This is where Dad works.
This is where my father works. That's my father's car. Way over there. That dorkmobile. Hello, Mr. Cohen. Can I call you Mr. Cohen?
You can call me Mr. Cohen or Daddy, your choice.
Hello, Mr. Cohen. Can you please give me a brief job description?
A brief job description.
Yes.
I'm a senior systems engineer, and I do two primary things and a couple of other things. But the two primary things I do is systems design, and that's looking at customers' specifications and figuring out how we can meet their needs. And the second part is control systems engineering, where I write software and work with control algorithms to help point these positioners at the targets.
What does this company do?
At Cobham Defense Electronic Systems Atlantic Positioner Systems Division, we build robotic positioning systems to point things. Things like communications antennas pointing at satellites, or video cameras pointed at surveillance targets, things of that nature.
Okay.
There's some positioners like this one have the things they point on the outside.
Now make it move. Make it move. Okay. I think that's enough. You? Okay.
Some are little and point little things. Some are bigger and point bigger things.
And what are the educational requirements for your particular job?
For my particular position, you need a Bachelor of Science in some engineering discipline, probably either mechanical or electrical engineering.
Okay. And that's all we have for the questions. Then we're going to... Oh wait, can you give me one specific example of how you use math in this particular job?
Well, one problem that we've solved from time to time is that a customer's requirement will say a positioner has to be able to point in one direction and then turn around 180 degrees and point in another direction in some period of time. And so calculating how much torque, which is the measure of rotational strength a positioner has to have on that axis, is one of the problems we solve fairly regularly.
Okay.
Okay, so to figure out the torque that we're going to need to make a system turn around in a given period of time, we use what's called the fundamental equation of rotational motion, which says that the torque is equal to the inertia times the acceleration plus the friction. The friction times the velocity plus the spring constant times the position plus something called Coulomb friction, or Q. Fortunately, for most of our systems, the B, K, and Q are very small numbers. So the J term is the biggest one, and that's all we really need to worry about. So for most of the jobs, we can just be a little lazy and get rid of all of these guys. So what we're left with is that the torque required is equal to the inertia times the acceleration desired. Okay. Inertia is the resistance to rotational change. As you know, inertia is the tendency of a body at rest to remain at rest, or a body in motion to remain in motion. It's the same thing for rotational systems as it is for linear systems, and inertia is the resistance to rotational change. So for our problem, we'll say that we've got a system that has a 20 kilogram meters squared inertia, and we want to rotate it, make a full rotation in 180 degrees, and we want to do that in, let's say, 2 seconds. Okay, so now all we have to do is plug in the acceleration we need, but we don't have an acceleration here. All we have is a distance that we want to travel. Okay, so if we want to travel to 180 degrees, we're going to accelerate for half of the time and then decelerate for the other half of the time. So if we accelerate as hard as we can and then decelerate as hard as we can for each for half of the time, we will have turned the full 180 degrees. So we've got to figure out how fast we need to accelerate to go half of this distance in half of the time. So acceleration velocity. We can get the velocity from the acceleration by taking the velocity, or the acceleration rather, and multiplying it by time. But to get the position, we have to integrate, unfortunately, the velocity with respect to time. So the position will be equal to the integral of the velocity, which is the acceleration times time, as we said before, with respect to time. Doing this integration, we get that the position is equal to the acceleration times the time squared over 2. Okay, so now we know how to get position. We come back to our original problem. So what we really wanted to do, you'll remember we're going to turn halfway at full acceleration and then decelerate for the second half. We say we want to go 90 degrees in 1 second. Okay? It won't come out the same as 180 and 2 is different than 90 and 1 because of the squared term. Okay? So we'll go ahead and plug in the 90 degrees in 1 second. So we'll say we want to turn 90 degrees is equal to theta dot dot times 1 squared over 2. Multiply both sides by 2. We get 180 is equal to theta dot dot times 1 squared. 1 squared is kind of dumb because, well, that's just 1, so we'll ignore that. So the acceleration required is 180 degrees per second squared. Unfortunately, this equation is assuming that the acceleration rate is given in units called radians, not in degrees. So there's a simple conversion to go from degrees, 180 degrees, to radians. And that conversion is that 360 degrees is equal to 2 pi radians. Okay? So substituting that in down here for the 180, we'll say 180 times 2 pi over 360 equals the acceleration that we require. Okay? 180 over 360 is 1/2 times 2 pi, so it's equal to pi is equal to theta dot dot. So we need to accelerate at pi radians per second. Okay? I'm sorry, pi radians per second squared. So now we feed this back into our original equation, and we know that the torque we need is equal to J, which we have is 20 kilograms meters squared, times the acceleration we need, or pi. That's the ugliest pi in the history of mathematics, times pi. So we need 20 pi Newton meters of torque to accelerate our 20 kilogram meters squared inertia payload enough to rotate it 180 degrees and stop in 2 seconds.
Okay. Okay.